one is there is a bias in the estimate, and other one is the variance in the estimate. So let us understand what is this, what are these two terms. Now this bias is because of the limited, no, it is you are observing only a few training examples. So it is limited by the number of example set on which you are measuring this accuracy. So if we consider the larger population, and if you consider randomly different kind of different kind of instances, there different instances from that population, this measure may not be the same. So what is the reliability in that case? And particularly if you have a rich hypothesis space, uh, then this is a problem, because as you know, rich hypothesis means there are many consistent hypotheses with respect to your training examples. So, but your objective is to get the target function, so hypothesis which is very close to the target function, or which is exactly the target function. If it is already uh, already included in your hypothesis space, you would like to get the target function as your hypothesis. So that is the issue, and that's why we are for accuracy, for estimating accuracy, we give more credibility or more emphasis on the test accuracy rather than training accuracy, even the validation accuracy. So when you build up a model, you look at training accuracy, and then of course you look at validation accuracy. But finally, when you are comparing two models, then you should compare based on test accuracy. So that is what one of the measures that is taken here. And variance is in the estimate. You would like to know that given the variabilities in the data set, with different with the different variations on the data set, I should say that because you are getting you are looking at only a few training examples. Now, it may not capture the whole variation. So how this estimate will vary with respect to different data sets. So smaller the size, you are expecting these variations will be also larger. That means your accuracy, it's a point observation that you are getting with respect to a particular set of examples. But if you have an idea that what could be the ranges with your estimations, if you can have some theoretical understanding of that range of variation, that would give you a better, I should say, better better measures for judging that how good is your hypothesis. So there are two key questions here that as you see that what is the probable error in the estimate of accuracy? That means what is the probable range of estimates? So that true estimate lies within its within the probable. So first is that what could be the best estimate of accuracy of H? As you have seen that given a hypothesis H over n examples randomly drawn from a distribution, what is the best estimate of accuracy? So there could be different kinds of estimates. And then what is the probable error in the estimate of accuracy? So let us define a few terms, like while addressing this particular issue, that how do you measure the error of a hypothesis. Consider these definitions. You know that you are handling an instance. So let us denote it by the that symbol X, and we know that it's an element of the domain D. That means the population D. And then S is a data sample, means it's a set of training examples, and its size is n. And you consider your hypothesis in this form. That means you are restricting your hypothesis in this case as a two-class classification problem kind of thing. So your target function can map to a value only either 0 to 1. So we are considering this special situation in this case. And you also so that is what your hypothesis is in this form. Similarly, your target function should be also in the same form, that it's also a function from from the set of instances to this 0, 1. And then you consider an error function. Now, this is a definition here that you are simply defining that if x and y they are same, then it is 0. That means x and y is the output. In this case, it is basically elements of the output set. That means in this case, x could be either 0 or 1, or y could be either 0 or 1. So if they are same, then definitely there is no error. That means your target function value and your hypothesis generated value, they are the same. So you get an error 0. Otherwise, the error is 1. So with this, we define sample error. It's very simple. It's basically the average or the fraction of samples, fraction of instances where there is a difference of observation between hypothesis and your target function. So, so that is what your so it is a relative proportion of your error number of cases where you are getting different values, different than the target function values. So this is, since you are observing over the sample space, so we call this error as sample error. But with respect to your hypothesis, if you consider the whole population, that means the domain D, and then we define it in a probabilistic way, that what is the probability that they differ. So that is the definition, probabilistic definition, and that is what is the true error. So our objective is to estimate true error, and what we can estimate sample error, but now how it relates with true error. That means whether we can provide certain bounds on sample error using sample error, so that the true error lies within that interval, within that bound. And we'll see that there is a concept called confidence interval that will come. And using that kind of analysis, we can see that how the hypothesis will, we can judge the performance of an hypothesis. So this is the, I should say, simpler or reduced definition of sample error, what we have shown in the above, here. That means using that summation symbol. Instead, we just say that if there are cases of error, are erroneous cases, then given n samples, that is the size of the data sample, your fraction of times, that is r by n, this error occurs. That fraction is your sample error. Right. So now the theoretical questions that, of course, the first thing is, okay, this answer is simple. That means we have already defined that given r errors in n samples, there is a rider n greater than equal 30. It has certain meaning. So let us ignore that initially. Let us go by the definition that ESH equals r by n. Now, given no other information, what is the most probable EDH? That means what is a true error in that case. So if you have no other information, you can say from the statistical theory, we can show it that actually your sample error is your that most expected value from the probabilistic sense, most expected value of the of your that EDH, that means the true error, is actually your sample error. And with approximately 95% probability, these are the results I'm telling you, but now we will have its interpretations later on. This EDH lies within this limit. Okay, so so can you tell me that why it is so? Can anyone explain me? It will take some time. So actually, let me give you.
This is the like we calculate confidence in this way actually.
Yeah.
Like, right. And this error of h into 1 minus error of h by n. This approximately, they're approximating the variance by this actually.
This root over is the standard deviation.
Yeah.
Did you get this term earlier? ESH and 1 minus ESH, what it is? See, ESH can be considered that parameter. Suppose it's a Bernoulli. I told you that if you consider a Bernoulli distribution, that is the event, single outcome. So um, what is the most expected error? What is the estimate of the parameter P if you have a Bernoulli distribution? So given R cases of error on n trials, so expected value would be R by n, right? That is equal to P. P is the fraction of time that probability there is an error with n observation. So given that experiments, you have R failures, right? So the probability of error of failure is P, which is equal to, which is an estimate. ESH is giving that estimate. We'll come to that part. That expectation of the of that P. P is basically would be R by n. We have, if you go through that probability theory, we already given that introduction. But what is the variance? If it is P, what is the variance of a Bernoulli experiment?
P into 1 minus P.
Exactly. So you see that numerator is something like this, P into 1 minus P. But no, there is a central limit theory because you are doing on n samples. If you consider each experiment independent, then actually the standard deviation would be this. The variance would be that divided by n, and then you get the square root. So we'll come to the central limit theory later on. So you see that then the other interesting fact is that when you are taking this estimate as an average of all, these events. So then using central limit theory, you can show that it is following a Gaussian distribution. And since this follows a Gaussian distribution, you have this particular confidence interval. I will again explain. This is coming in my subsequent slides. So I hope this expression is now at least clear to you. The explanation may not be, but expression is clear to you. So which means now if I give you corresponding R value of R and N, and actually it can be shown that this is valid when N is greater than or equal to 30. There is a reason for that. So we have this confidence interval. So this is the thing that above approximation works well when this is true. And for example, if your ESH is 0.213 or lower, then you should have if your ESH is 0.213, then minimum N should be around 30. And as you can see that if you take higher error, basically lower the error, you need more number of samples. Lower the estimate of your error, you need more number of samples. So smaller estimate value requires larger sample size. That is the kind of way. So that's some example like N equal to 40 and R equal to 12. So you have this corresponding estimate of your sample error is 0.3, which is also the estimate of your true error, but your confidence interval would be this. It is using that computations. That means though you are getting an estimate of 0.3 in your, suppose you did this kind of validation test, and you finally you perform this test accuracy. You on the test data you got this accuracy. That means accuracy here is say 0.7. 0.3 is just the opposite, it is the error. So in that case, you can say that your true error would lie between 0.3 and 0.14 if you have if your training examples has 40, that size of your training data set is 40, then you can have this kind of confidence interval. So which means your true error lies within this interval 0.16 and 0.44, but there is a probabilistic interpretations that with 95% probability. With 95% probability, it lies within this. Okay, and we can say also with 97.5% probability, it is less than 0.44. I think you understood this part also. If you consider, as I mentioned, it's a Gaussian distribution. This estimate has a Gaussian distribution. So it's symmetric. It is symmetric. So 5% probability that is outside this range, it comes from the lower end tail and also higher end tail, each divided into 2.5% zone. So this is a schematic diagram. At the top, you can see that the shaded portion is the probability of the interval. That area gives you the total probability of the confidence interval, and outside it is the probability outside this interval. That it will lie outside this interval. That those are the probabilities. So there is a lower range, there is a upper range. So as I was mentioning that from the properties of binomial, and which is normal for large n distribution, you have this particular analysis. So let us consider this, that probability of error for a sample is P, and that is how the analysis is being shown. Is being shown here. Probability of R errors in n sample is this, and then expectation of the number of error R is NP, and variance of R is n into P1 minus P. So in that case, expectation of R by n is equal to P, and then we say that estimate of P is your is the unbiased estimate, because expectation of your measure is the true estimate. It is equal to the true estimate of the parameter, whereas variance of P can be shown as variance of R by n, and as you know, this is a simple algebraic manipulations, that if variance of the variance of R is n into P into 1 minus P, so variance of R by n would be that divided by n square. That you can easily check. So which is P into 1 minus P by n, right? So even without going into central limit theory, just using binomial distribution also you can show this is what is the variance. But finally you are approximating it as a Gaussian distribution, and then you are putting those limit. I mean that 1.96 into root over of that. So bias of the estimate, as I mentioned, expectation of the estimate minus true parameter value. So what would be the bias in this case? Bias of the estimate in this case?
0 actually.
It is 0. It is unbiased estimate. And of course, there are inductive bias. Now, inductive bias and bias of estimate is different. Bias of estimate is definition is this. That means in the estimate, what is the deviation of its expected value from the true value. Whereas inductive bias terms comes from that assertions due to when you are making inductions. What are the assertions? And bias of estimate is a numerical quantity. It just shows you the kind of differences. So next come to this definition of confidence interval. I just mentioned it, say 95% confidence interval. So in general, we can say n% confidence interval. So its definition, theoretical definition is that it is the interval containing the true value with probability n%, right? With probability n%, that is n% confidence interval. And as you know that for large sample, binomial distribution approximates normal distribution. So you get this you get this kind of representation. Say the normal distribution we can denote it by these two parameters, mu and sigma. Okay, so and you know that at mu you get the maximum probability for the probability density function. So for the probability density function, the maximum occurs at mu, and the probability of any interval is the area under that curve. Now Zn sigma is the offset from mu, towards increasing direction, or also you consider the other, Zn sigma is the offset towards the negative direction also from mu. So the values, the interval is defined. What is the interval in this case? What is the interval we are trying to show in the figure?
Mu minus Z
2
sigma
sigma.
Pardon?
plus
Cannot hear you. Can you repeat?
An n% confidence interval, right? We are trying to show.
N% confidence interval, this n is not that n there is normal distribution. I will come to that n% thing later on, but no, I am just asking from this figure, can you tell me what is the interval it is denoting? That shaded region, it is denoting an interval of the random variable. There is a lower limit and higher limit. So what is this lower limit and what is this higher limit?
Nu minus sigma to nu plus sigma.
Not minus sigma plus. It is mu minus Zn sigma to mu plus Zn sigma. So that means Zn is a scale factor with respect to sigma. Like 1.96, right? When it was Zn equal to 1.96, then interval was mu plus 1.96 sigma, mu minus 1.96 sigma. Is it clear now? So this n%, that depends upon the factor Zn, because no, normal distribution is it is well defined, and no, you can always define, because you can normalize it, right? Which means that which means what? That if I normalize this distribution where mu equal to 0, that means where expectation of distribution is 0 and sigma equal to 1, then what should be this interval in the normalized case? That means I make this random variable as x minus mu by sigma. Then what should be this interval?
Minus Zn to Zn.
Exactly, minus Zn to Zn. So you see that we have normalized it. So minus 1.96 to 1.9. Now that, if you consider the sum of area of curve under that interval, then that value would be n, capital n%, I should say, not capital n%, because it, no, you know that sum of area is 1, so it has to be like a fraction. So that value is n%. So which means if I consider the distribution as standard Gaussian distribution with 0 mean and standard deviation 1 or variance 1, whatever you can say, then the probability of the interval from minus 1.96 to 1.96, the probability of a random variable having a value between minus 1.96, within minus 1.96 to 1.96, what should be that value? What should be that probability?
0.95.
0.95. That is what is called 95% confidence interval. Do you understand now what is meant by this n% confidence interval? So when you are giving an estimate, you are not only just giving that point estimate, you are also giving an interval. And your estimate, somehow your estimate follows a normal distribution. There is a reason for that. Most cases your estimate will follow a normal distribution. And in that case, you are giving that interval because it follows a normal distribution, it is easier to give. You can give this 95% confidence. In general, there is a general definition, but mostly it follows a normal distribution, and we express in this way. So this is what your confidence interval in this case, mu plus minus Zn sigma. And you see this table, it shows that if you increase the value of n, actually this Zn increases, because no, you are increasing the width of your interval. That means your measurement is more imprecise. Naturally, you are making sure that what is the so for example, if I consider your true error lies within minus infinity to minus plus infinity, what should be the probability? Probability should be 1, because it's a real value, right? Something like that. So if I give you an estimate, then if I can give you this interval and narrower the interval, more precise is the estimate, and higher the probability. Narrower the interval, higher the probability within that interval, your estimate is more robust and reliable. I hope this is clear. So now the question is that so let us consider this a general approach for deriving confidence interval of an estimate. Many of you have already implemented your this decision tree, and I am sure that you have considered several competing hypotheses in terms of pruning nodes, etc. But maybe you can have a relook that how you have compared them there and how actually you should do it in a more robust way. So this algorithm tells you that. So let us go through these steps. So consider this, say y is the estimator of a parameter p. So in this case, no, your parameter p is that accuracy, right? Your measure of accuracy or measure of error, whatever way you can define it. Then you need to determine the probability distribution dy of y and its mean and variance. You should determine the n% confidence interval using mean and variance. Now, if you know the functional form of the probability density function, then only you can do that. Otherwise, no, it is difficult analytically. And by finding thresholds L and U such that n% mass of dy falls between L and U, and of course your estimate mean should lie within L and U, then you can declare that interval. Now there comes the applicability of central limit theory. Sorry for the spelling mistake here. So I hope I will correct it while uploading this slide. So the estimating mean of distribution. So what is interesting is that since if you are estimating mean of any distribution, and then if you apply the central limit theory, then you can always model it under a normal distribution. That estimate itself will follow a normal distribution. So let us see what is the central limit theory. So the central limit theory says that suppose you are estimating mu. Suppose you have a distribution of y that is the measure what you are going to estimate, and it follows a distribution with mu and sigma, and mu is the mean, which means which is the expectation. So in the statistical term, in the probabilistic term, mean is equated with expectation. As I mentioned, it is a weighted average where weights are probabilities. So mu is expectation of y, and sigma square, sigma is the variance of the distribution. It not necessarily it has to be a normal distribution. You should understand that. So d mu sigma is not necessarily is a normal distribution. It could be binomial. It could be any other kind of distribution, Poisson or any other kind of continuous domain distribution also. Now you consider n independent observation of y, which means you are observing, you are estimating y more number of times with independent set of experiments. Say you are considering measurement of accuracy, this k-fold cross validation, that which means you are doing k times. You are doing k times with k-fold cross validation. I think you are doing k times, isn't it? You are k times you are measuring the accuracy. Is it? Am I correct? Any confusion?
Can you repeat once more, sir?
So suppose you are doing k-fold cross validation. You understand what is meant by k-fold cross validation? Which means you partition your training examples. I mean, you keep aside, you partition your training examples into k partitions. Use k-1 partition, k-1 partitions as your training set, and the rest, one of them as the validation set. The other set as the validation, and you can measure the accuracy, validation accuracy. Is it clear?
Yes, sir.
And you do it for k times, because every time you can select one partition as your validation set. So there are k such choices. So you do it k times. So that means you have k independent measures. Though you have selected randomly partitions, etc. So independence is something that is assumed also but more or less it is independent. So if you have this kind of node, so you have k independent observations. So then what are you doing with all these observations? So actually, what are you doing now? You have already implemented, some of you, if you have implemented this k-fold cross validation, What you did after that? Any one of you can tell me if you have done. Otherwise, I will assume you are not doing it.
We were comparing the averages.
Averages of all validation accuracies, isn't it?
Yeah.
Yeah, exactly. That is what it is telling. That you should do it. That you should take the average, and that average will give you the estimate of mu, and that is an unbiased estimate. But you are not computing what is the interval. What is the 95% confidence interval centering that average? That you are not computing, isn't it? Are you computing? So that you should do. That is what it is saying. So it is average, and then no, you know that this distribution, that is the interesting part, that mean, when you consider the actual variance is sigma of the population, but if you consider the distribution on the average, then actually it becomes a normal distribution following the central limit theory. Then the distribution is not D. Distribution of that estimate, that average, is a normal distribution whose mean is again mu. So, that is the interesting part. So y1, y2, yn, these are your now, as if these are your observations. Now you are estimating mean of that population. So mean ya is the estimate of mu itself. And what is the variance of ya? It is sigma by root n. So this is what, right? So you find out what is the what is the corresponding variance of this sample set yn. So the variance of measure of y1, y2, yn, that you can compute. You can estimate the variance from the measure from your accuracy set. And if there are k, if there are k observations for k fold, so what should be the value? Sigma by root k. Suppose sigma is the standard deviation. Sigma is the standard deviation. Sigma square is the variance. Then sigma by root n should be the standard deviations. So this will follow the normal distribution. This is what is central limit theory says, and which means that I will use that sigma by root n as the variance. So this is what, when you compare two hypotheses, you should take the difference of their errors in the distribution D and observe D while they are tested on two independent samples, S1 and S2 of size. As you say, as we have said, that to make it reliable, the sample set should be greater than equals 30. So you should observe it, and then expectation of D prime equals D, and the variance would be this. Variance would be this. This is coming from binomial distribution also. It is coming from that also. Variance would be this, and then they follow the normal distribution. So the variance of D dash is the sum of variances of ESA, S1. This is what. So finally, it is a difference that would give you the interval. So why I have given this kind of measure instead of just computing averages? Because I'm comparing two hypotheses, and I am finding out the difference what you get between these two accuracies. Suppose you have pruned a tree, okay, decision tree, and you have the other hypothesis is a full tree. So you have computed the accuracy with full tree. You have computed the accuracy with this. So here actually we are computing errors in this case. We are computing the errors with the full tree, estimate of the error, and you have computed the error of the pruned tree. That is another hypothesis. Now you observe that suppose your error is reduced in the pruned tree. Just that's a point observation. But if I consider any random case, how many times it would be, say it may also, sometimes it may be also greater also. So what is the interval within which this error will lie? If this difference will lie rather. If this difference is always positive, then we can say with 95% surety, if the Zn is 1.96, with 95% surety that your your competing hypothesis is better than the other. One of them is better than the other, depending upon which has shown less error. Did you get my point?
Yes, sir.
Okay, so this is how you should do while evaluating the hypothesis. As I said, this is n% of confidence interval. So this is the question. As I mentioned, just figurative explanation that no, you are estimating d prime, and then you observe the interval on which this d prime will lie. And if your d prime is greater than 0, with this confidence, you can say that the range lies in the positive side. So we are more interested on that part. And then we can say that H2 is better than H1 because no, if this is satisfied, then we say that H2 is better than H1, and you can take H2 than H1. Right? So that is what I just mentioned. So you have till 2 or 3 more days. So you may try to refine your algorithm using this theory and see whether you are getting some changes in your results.
Sir?
Yeah.
Yeah, so okay, so small clarification needed. Okay, so for in assignment for pruning, we did sort of exactly what you explained today. At the start of the assignment, for different depths, they told us to calculate average accuracy and then choose the best depth. For that, we should directly choose, right? No need of this confidence
that
interval.
is fine. See, whatever it has been told you, you please do it. That is not an issue. I'm just telling you, you can refine it wherever it is applicable. So, see, one of the objective of this assignment is that for your learning also. You observe, you learn. We are not expecting that no, you have to come up with a very good scheme with very good high score, etc., etc. That we are not asking you to do. But eventually, no, you have to adopt these policies, these approaches, so that no, you can apply it in real scenario to get improved performances, etc. Okay, so many of you have asked this question about EEG that no, these variances they are not giving good results. They won't. We have simplified that means that's a very complex, the challenging issue to make to select appropriate features which will give you good performance. But we are not going to give you an assignment, and we are not going to give you a research problem on that. So we are trying to set your assignment based on what is being covered in the class, so that no, you can apply that knowledge and you can implement something, you can see some result. It is not that no, you are expecting you will get 80%, 90% accuracy, even it is 20%, 30%. If you follow your correct methodology, that is fine for us. Okay? But no, you should understand the challenges. Yeah.
Excuse me, sir. So one more thing.
Right.
Sir, there are 3 .eda files in that EEG data set. If we are converting them to .csv, then they are giving very small values, like they are in the 10 raised to power minus 8. So that's becoming a problem. And if we try to convert them through that, then whole tree will fall and it will not give any accuracy or any result after that. Information game also becomes negative at that time. So
see, these are all distributions.
Can we remove?
These are all distributions. No? I mean, you can think about some normalization, some scaling if you require.
Sir, can we remove those 3 files if it's possible? Because they are only those 3 files are making the whole tree redundant.
Yeah, you explain. You give the explanation. See, we are not interested on those intricacies, because if you can compute those 14-dimensional feature, if you can build up a decision tree, if you follow the method, we are more interested on that, as you can understand. So if you can do that thing, I think Ankita has already explained to many of you that no, you do what is being told first, and then whatever you feel appropriate, please mention that, and you can also include that. That would be appreciated. Okay?
Okay, sir. Thank you.
Okay. So this is what, now if you compare the performance two learning schemes, so this is actually the k-fold thing, what I just explained, this k is coming from there. So if you, it is just simply, it should be sigma y by, actually no, the other thing is that sometimes this distribution may not be exactly normal for a limited observation if you have a less number of samples. So there is a distribution called students t distribution. So that t distribution may be used, and that sigma y by k, I think that should be root k. There is some error. Sigma y square is 1 by k minus 1. Yes, sigma y by, that should be by root k. So there is some error in my slide. I'll check that and I'll update it. So you please note it down. But no, here what we are saying that in some cases, the normal distributions, if you have too small, not many samples, it is better to use these t distributions. With t distributions comes with the number of samples. It is tied with the number of observations, number of samples, and there is k minus 1 degree of freedom. And each one will have a different distribution. So there is a functional form. So there is a statistical table which one needs to consult from the practical point of view. And from there, you can get this n% probability sum within that interval. In fact, as k tends to infinity, this is going to be a normal distribution. So definitely this is an error, the sigma y by k, what is shown here. So you have to make it square root. So this is just a repetition. I am not going to, I'll just simply show it. Do you have any questions? Let me know. The last sentence is very interesting. You see a lot of papers, they simply report the average accuracy. A lot of papers, I think including mine also, you might find. But we should not do that. Okay, so from now onwards, please use this kind of statistical analysis. So the summary of this particular topic is that you have the unbiased estimate of error as a fraction of test samples not satisfying target function, which is this. And then you can compute its variance, which is given by this. This is again something wrong. Variance would be actually divided by n. I have to again rectify that. So this estimate, the variance should be divided by n. This should. Then n% confidence interval defined using them, you can do that. Then we can evaluate computing hypothesis by using the probability distribution of the difference of errors. And you can apply central limit theorem using for estimating average of a statistics. We have seen the significance and importance of central limit theorem, which has simplified our job of computing confidence interval. And you can use this same approach in k-fold cross validations. As I mentioned that instead of Gaussian, you can use also students distribution, students t distributions when you have limited number of samples. So with this, let me stop this particular topic.